Mars is a silent desert waiting for a sky. The monumental planetary engineering required to forge a breathable atmosphere there is the ultimate test of our species. By the end of this, you will understand the staggering scale of turning a dead world into a living one. How do you make an entire planet hold its breath? And what ancient force is actively trying to strip that air away? This journey will reveal technologies that bend sunbeams and armies of machines that think for themselves, all to answer one profound question. What does it truly mean to build a future from scratch? That missing sky is the first and greatest obstacle. Standing on the surface of Mars, you would not feel a breeze or hear a whisper because the air is simply not there. The atmospheric pressure is less than 1% of what we experience at sea level on Earth. To find a similar pressure here, you would have to climb to an altitude of over 20 miles, far above where commercial jets fly, into a near vacuum. This thin Martian shroud is not just sparse, it is also poisonous to us, composed almost entirely of carbon dioxide. The tiny amounts of nitrogen and argon present are mere traces, and the oxygen we need to breathe is essentially absent. So the challenge is not merely to thicken the air, but to completely reinvent its chemical recipe. This profound emptiness is the result of a slow, cosmic robbery that has been ongoing for billions of years. Mars, lacking a strong global magnetic field and possessing only about a third of Earth's gravity, has been largely defenseless against the solar wind, a constant stream of charged particles from our Sun. Over eons, this wind has steadily eroded the planet's once thicker atmosphere, molecule by molecule, stripping it away into space and leaving behind the stark, exposed world we see today. Therefore, the task of forging a breathable atmosphere is not a simple act of addition. It is a race against a fundamental planetary condition, a fight to create and hold onto an entire sky against forces that are actively working to take it away. This brings us to the staggering first question of the project. How much air exactly are we missing? The gravity you feel on Mars is a gentle pull, a whisper compared to Earth's firm embrace. This fundamental difference is the source of our first monumental engineering puzzle. We are not just tasked with building an atmosphere, we are tasked with building one that will stay. Think of a planet's gravity as a kind of cosmic hand holding its blanket of air close. Mars's hand is weak, only about 38% as strong as Earth's. Over immense stretches of time, the lighter gases in an atmosphere, like hydrogen and helium, can slowly drift away from such a gentle grip. But for the heavier gases we need, like nitrogen and oxygen, this weaker gravity is a manageable, long-term concern. The real, immediate threat is something far more aggressive. Mars is naked before the Sun. Unlike Earth, which is cocooned within a powerful, planet-wide magnetic field generated by its churning molten core, Mars has only fractured, localized remnants of its ancient shield. This means the solar wind, that relentless stream of high-energy particles flowing from the Sun, strikes the Martian atmosphere directly. It acts like a cosmic sandblaster, striking gas molecules with enough force to knock them free from the planet's weak gravity and send them spiraling off into the void. This process, called atmospheric sputtering, has been stripping Mars bare for billions of years, so our challenge is dual in nature. We must become both creators and guardians. We must find a way to generate trillions upon trillions of tons of new atmospheric gases, a number so large it defies everyday comprehension, and simultaneously, we must find a way to protect that colossal investment from being stolen away. One theoretical solution sounds like pure science fiction, reigniting the planet's molten core to spin up a new magnetic dynamo. The energy required for such planetary-scale surgery is for now beyond any conceivable technology. A more plausible, though still staggering, proposal is to build an artificial magnetic shield. The idea is to place a massive structure, essentially a powerful magnetic field generator, at a stable gravitational point between Mars and the Sun. This magnetic bubble would act as a kind of umbrella, diverting the solar wind around the planet and allowing any atmosphere we build to accumulate and stabilize. It is a concept that shifts engineering from the planetary surface to the space around it, a reminder that taming a world requires thinking on a solar system scale. This foundational dilemma teaches us a critical lesson before we even begin to talk about making air. Planetary engineering is not just about production, it is fundamentally about protection. How we solve for this relentless erosion will dictate every step that follows, especially the next colossal question. Where on Earth, or rather, where on Mars, do we possibly find the raw materials for an entire sky? The raw materials for a new sky are already on Mars, but they are prisoners. Oxygen, nitrogen, and the inert gases that make an atmosphere stable are not floating freely for us to collect. They are bound within the very bones of the planet, locked in the icy grasp of the polar caps and chemically shackled within the rusty soil. Our task is to become planetary alchemists on an unimaginable scale, breaking these ancient bonds to set the building blocks of air free. To even approach a thin, breathable atmosphere, we would need to process a volume of material so vast it is difficult to conceive. Picture a layer of carbon dioxide ice covering the entire surface of Mars, several meters thick. That represents the sheer mass of gas we must somehow release, purify, and manage. This is not mining in any traditional sense. It is the systematic deconstruction of a world to build a new one from its pieces. The most obvious vaults are the polar ice caps. These gleaming white regions are not just water ice. They are layered with vast deposits of frozen carbon dioxide, what we call dry ice. One potential method to unlock this frozen reservoir sounds deceptively simple: make Mars warmer. By using enormous, thin-filmed mirrors placed in orbit around the planet, we could focus additional sunlight directly onto the polar regions. This concentrated solar energy would sublimate the dry ice, turning it directly from a solid into a gas, thickening the carbon dioxide atmosphere dramatically as a first step. It is a form of planetary-scale climate engineering, using mirrors to tilt the thermal balance of an entire world. The energy required to build, launch, and position such a solar fleet is immense, but it comes directly from the Sun, a nearly infinite power source if we can learn to harness it at that magnitude. Yet carbon dioxide alone is not a breathable atmosphere. We need oxygen, and for that we must look down at our feet. The Martian soil, its regolith, is not merely dirt. It is rich in iron oxides, the compounds that give the planet its distinctive red hue. These rust-colored minerals are, in essence, iron married to oxygen. To get the oxygen out, we would need to deploy armies of autonomous processing factories crawling across the Martian plains. These machines would scoop up the soil, heat it to extreme temperatures in contained environments, and use chemical or electrical processes to break the iron-oxygen bond. The liberated oxygen would be collected and stored, while the leftover metallic iron could become a valuable construction material. This process, however, is brutally energy-intensive. Each breath of air would be literally baked out of the ground, requiring a sprawling industrial infrastructure powered by vast fields of solar panels or perhaps compact nuclear reactors. Nitrogen presents a trickier puzzle. It is far less abundant on Mars, existing only in trace amounts in the atmosphere and possibly bound within nitrate deposits in the soil, a legacy of ancient atmospheric chemistry. Sourcing enough nitrogen to act as a crucial buffer gas, making the oxygen atmosphere stable and safe to breathe, would require a relentless global prospecting and extraction effort. It may become the limiting resource, the rare ingredient that dictates the ultimate capacity of our new atmosphere. Each of these pathways, from orbital mirrors to soil processors, frames the next critical and practical question. With such astronomical energy demands, where does the power for this century-long project actually come from? The opening act of forging a new sky would be a silent ballet of light. Enormous, gossamer-thin mirrors, each spanning hundreds of kilometers, would unfurl in the stillness of Martian orbit. Their purpose is elegantly simple: to catch the sun's rays and redirect them, like a magnifying glass focusing a beam onto the frozen poles of the red planet. This is solar forcing, the first gentle nudge in a planetary scale transformation. The goal is not to melt everything at once, but to initiate a carefully controlled chain reaction. By bathing the polar caps in this concentrated sunlight, we would begin sublimating the vast reservoirs of frozen carbon dioxide, turning dry ice directly into gas. This released carbon dioxide would thicken the thin Martian atmosphere, and as it does, a critical process would begin. Carbon dioxide is a potent greenhouse gas. A thicker blanket of it would trap more of the sun's heat, raising the planet's average temperature. This warming, in turn, would cause more carbon dioxide ice to sublimate, releasing more gas, trapping more heat, and so on. The hope is to trigger a runaway greenhouse effect, using the planet's own stored resources to do the heavy lifting of initial atmospheric construction. It is a concept of profound leverage, using the sun's infinite energy to unlock Mars's own vaults. The engineering of these orbital mirrors is itself a staggering challenge. They would need to be incredibly lightweight yet durable, able to maintain precise shapes and orientations for centuries. They represent a form of megastructure we have never built, a technology that feels more like art than engineering. Yet, compared to the brute force methods that must follow, this approach is remarkably elegant and low energy. It requires no fuel-burning engines on the surface, no armies of machines, just the patient, silent application of reflected sunlight. However, this delicate first step is fraught with risk. Planetary climate systems are unimaginably complex, and our models are based on a single data point, Earth. What if the warming accelerates beyond our predictions? What if it destabilizes the polar regions in unforeseen ways, or triggers the release of other, more problematic gases? This initial nudge must be calculated with extraordinary precision, for in climate engineering there is no undo button. A mistake here could render the entire project untenable, turning a dream of a new world into a cautionary tale of unintended consequences. But sunlight alone may not be enough to push the planet over the edge. After the initial warming from orbital mirrors begins its work, the next phase would require a more potent, more deliberate kind of alchemy. Engineers would transition from simply reflecting light to actively manufacturing climate. This is the amplification phase, where we introduce substances not found in nature, designed in laboratories for one specific purpose: to trap heat with ruthless efficiency. These are the super greenhouse gases, compounds like perfluorocarbons. To understand their power, consider that a single molecule of one of these engineered gases can trap thousands of times more thermal radiation than a molecule of carbon dioxide. They are also chemically inert and can persist in the atmosphere for centuries, making them a powerful, long-lasting tool. Their deployment would represent a point of no return, a conscious decision to chemically alter a world's climate system for millennia. The production of these gases would become a primary industry on Mars. Vast, sealed factories humming with activity would rise from the dust. They would be industrial behemoths, consuming colossal amounts of electricity to break apart and reassemble molecules sourced from the Martian soil and air. This power would likely come from fields of advanced nuclear fission reactors, their compact cores generating the steady, immense heat and electricity needed for continuous chemical synthesis, or from continent-spanning solar arrays that turn the weak Martian sunlight into the currency of planetary change. These factories would not have smokestacks in the traditional sense. Instead, they would have carefully controlled release vents, pumping their synthetic product directly into the thickening atmosphere. Each release would be a calculated act, monitored by a global network of sensors watching for the precise climatic response. The goal is acceleration. By artificially boosting the greenhouse effect beyond what the native carbon dioxide can provide, these super gases would act as a thermal catalyst. They would raise the global temperature more rapidly, melting more water ice and sublimating more frozen carbon dioxide from the poles and the soil. This releases the planet's own stored gases, creating a positive feedback loop that the super gases initiated but the planet itself sustains. It is a demonstration of guided leverage, using a small amount of human-made substance to unlock a far larger reservoir of planetary resource. This phase moves terraforming from a passive, observational science to an active, interventionist engineering discipline. It reveals the project's true nature as a series of escalating commitments, each stage requiring more energy, more infrastructure, and more precise control than the last. We are no longer just nudging the climate, we are deliberately tipping it into a new equilibrium, a warmer, wetter state that has not existed on Mars for billions of years. And as the temperature climbs and the ice retreats, a new and ancient substance would begin to flow across the rust-colored landscape, introducing the next profound element of change. A warm, thick sky of carbon dioxide is still a suffocating one. Transforming this global blanket of poison into a breathable atmosphere is the project's most profound chemical challenge. We must perform a planetary-scale magic trick, pulling the oxygen we need directly from the carbon dioxide we have in overwhelming abundance. This is where biology and industrial chemistry would have to merge, not in a lab, but across an entire world. The most elegant solution is also the oldest life has ever devised. Imagine seeding the newly thawed Martian lowlands, the damp soil and shallow, briny pools with a specially engineered form of life. Cyanobacteria or perhaps extremophile algae, organisms whose very purpose would be to breathe in the carbon dioxide and exhale oxygen through photosynthesis. These microscopic terraformers would be designed for maximum resilience and efficiency, able to thrive in the still harsh Martian conditions. They would spread slowly, turning patches of the landscape green, initiating a gentle, biological conversion that could, over centuries, begin to alter the very composition of the air. It is a method that leverages self-replication, turning each new cell into a tiny, living factory. Yet, biology is slow and vulnerable. The process would be measured in geological time, and a single unforeseen environmental shift could wipe out entire colonies, setting the project back generations. For a faster, more controlled transformation, we would need to think in terms of pure industry. This path leads to continent-sized arrays of automated chemical processes, machines that would dwarf any city. They would be direct, colossal descendants of experiments like the MOXIE unit on the Perseverance rover, which demonstrated a key process on a tiny scale. These factories would work on a principle called solid oxide electrolysis. They would suck in the thick Martian carbon dioxide, heat it to searing temperatures, and use powerful electrical currents to split the molecules apart. One stream of output would be carbon monoxide, a waste product to be carefully managed or perhaps used as a rocket fuel component. The other, the precious prize, would be pure, breathable oxygen. The scale required is almost paralyzing to consider. To generate enough oxygen to matter for a global atmosphere, these processing arrays would need to cover areas the size of entire nations. They would form a sprawling, metallic ecology of their own, humming across the plains under the pink sky. And here we encounter the project's most formidable bottleneck, pure energy. The electrical demand for splitting carbon dioxide on this scale is beyond anything humanity has ever produced. It would require a power infrastructure equivalent to the total energy output of our entire current Earth civilization, multiplied many times over. This forces a stark choice upon the engineers of a new world. Do they pave vast deserts with advanced solar panels, accepting the limitations of the weak Martian sunlight and the planet's long, dusty nights? Or do they commit to building hundreds, perhaps thousands, of advanced nuclear fission reactors, compact powerhouses that could provide steady, immense heat and electricity anywhere on the planet, day or night? Each option carries its own astronomical costs and logistical nightmares, from mining and refining nuclear fuel on Mars to manufacturing and maintaining millions of acres of solar cells. But creating the oxygen is only half the battle. Releasing it into the atmosphere is a delicate act of planetary management. Oxygen is a highly reactive gas. If released too quickly, it could interact violently with elements in the soil, binding to minerals before it ever accumulates in the air. The process would need to be gradual, carefully synchronized with the rising atmospheric pressure and temperature to ensure the gas stays where we need it. This introduces a layer of global climate modeling of staggering complexity, where every new ton of oxygen released must be calculated for its impact on the entire system. We are no longer just building an atmosphere, we are conducting a symphony of gases on a world stage, where a single wrong note could mean starting the movement all over again. Oxygen may be the star of the show, but it cannot perform alone. A sky made of pure oxygen would be a death trap, a global tinderbox where a single spark could ignite a planetary firestorm, and where every breath would slowly poison the human body. For an atmosphere to be truly livable, it needs a quiet, stabilizing partner, a buffer gas to dilute the oxygen and make it safe. On Earth, that role is played overwhelmingly by nitrogen, a gas that makes up more than 3/4 of the air we breathe. On Mars, nitrogen is the forgotten essential, the scarce ingredient that could become the ultimate bottleneck in our entire endeavor. The Martian atmosphere contains only a faint whisper of nitrogen, less than 3% of its already thin composition. This means that while we are busy unlocking trillions of tons of carbon dioxide and oxygen, we must also embark on a parallel, silent quest to find and release a mountain of an entirely different element. Where could it possibly be hiding? The most promising vaults are not in the sky, but locked within the ground. Planetary scientists believe significant deposits of nitrogen may be chemically bound within nitrate salts in the Martian soil, a relic from ancient atmospheric processes or long-vanished liquid water. To access it, we would need to become planetary-scale miners and chemists. Imagine fleets of autonomous excavators, each the size of a city block, crawling across the desolate plains. Their mission would not be to find precious metals, but to process common dirt on an almost inconceivable scale. They would scoop up millions of cubic kilometers of regolith, feed it into mobile processing plants that heat the soil to extreme temperatures, breaking the chemical bonds to liberate the trapped nitrogen gas. This operation would be a monument to patience and energy consumption, a global industrial effort running for centuries just to source a single component of the air. The sheer tonnage of soil that must be moved and processed to yield a useful amount of nitrogen is a number that bends the mind, a reminder that we are not just altering a landscape, but systematically deconstructing it atom by atom. For some thinkers, the slow grind of soil processing is too limited. They look to the solar system's delivery service for a more dramatic, if terrifying, solution. The outer solar system is rich with icy bodies, comets and asteroids that contain frozen nitrogen and ammonia. One audacious proposal suggests redirecting a carefully selected, nitrogen-rich comet into a controlled impact on Mars. The collision would be cataclysmic, releasing immense energy and vaporizing the comet's ices, instantly injecting a massive pulse of nitrogen and water vapor into the atmosphere. It is a shortcut of staggering violence, a single event doing the work of millennia of mining. But the risks are as monumental as the reward. The impact energy would be equivalent to millions of our most powerful nuclear weapons detonating at once. It could trigger global quakes, throw up enough dust to plunge the planet into a decades-long winter, and utterly devastate any fledgling surface infrastructure we have built. It is the definition of a high-risk, high-reward strategy, a reminder that playing with celestial mechanics carries consequences we might not be able to control. This quiet search for nitrogen underscores a profound truth about planetary engineering. Terraforming is not one grand technology, but a symphony of 1,000 different projects, each solving for a specific critical piece of the puzzle. We must be masters of atmospheric chemistry, orbital mechanics, global geology, and energy systems, all working in concert. The nitrogen problem, often overlooked, teaches us that the most breathable sky is a balanced one, a delicate mixture we have never had to consciously assemble before. And once we have gathered the raw gases, an even more intricate challenge awaits, one of timing and global balance. How do we manage the release of these elements to build an atmosphere that is not only thick, but stable and safe for millennia to come? Water is the silent architect of a living world. Once the atmospheric pressure and temperature begin their slow climb, a hidden treasure will start to awaken across Mars. Locked away in the gleaming polar caps and buried in vast subterranean glaciers, the planet holds more than enough water to fill its ancient, dry riverbeds and crater basins. But unlocking this frozen archive and managing its flow will become one of the most delicate and transformative phases of the entire project, a branch of engineering we might call planetary scale hydrology. The goal is not merely to melt ice, but to birth an entire water cycle from scratch, coaxing rain from a sky that has never known clouds and guiding rivers across a landscape that has been bone dry for eons. This begins with the deliberate, controlled warming of the polar regions, likely accelerated by those orbital mirrors and super greenhouse gases. As the temperature rises, the frozen carbon dioxide at the poles sublimates first, thickening the air. Then, as the warmth penetrates deeper, the underlying water ice begins its change of state. This is where the engineering must become incredibly precise, because melting the poles too quickly could create catastrophic floods, sudden outbursts of water that would carve chaotic channels and be lost to rapid evaporation in the still thin atmosphere. Instead, the process would need to be gradual, almost seasonal, allowing meltwater to pool and spread slowly, raising the humidity region by region. But liquid water on Mars faces a fundamental physical challenge. Even with a thicker, warmer atmosphere, the surface pressure would remain far lower than Earth's for a long time. At low pressure, water boils at a much lower temperature. On early Mars, a puddle might simultaneously melt and violently boil away. To prevent this, the initial bodies of water would need to be managed, perhaps contained within vast, sealed catchment basins or shallow, rapidly expanding seas that increase local humidity and pressure, creating their own more stable microclimates. This is landscape engineering on a continental scale, sculpting drainages and shorelines to guide and hold the planet's most precious resource. As these first lakes form, they become more than just reservoirs. They become the cradle for the next stage of biological transformation. Imagine introducing specially engineered, hardy algae or cyanobacteria into these new, briny waters. These microorganisms would be designed with one primary function: to thrive in Martian conditions and metabolize the abundant carbon dioxide, releasing oxygen as a byproduct. A single thriving algal bloom could tint a new Martian sea green, and as it spreads, it begins a gentle, self-replicating process of atmospheric alteration. Furthermore, the presence of liquid water itself kickstarts crucial geochemical cycles. Water percolating through the soil would weather minerals, releasing trapped gases like nitrogen and altering soil chemistry to become more hospitable for future, more complex life. This creates a beautiful and powerful feedback loop. The atmosphere warms the planet and unlocks the water. The water hosts life that changes the atmosphere, and the altered atmosphere stabilizes the water. Each element reinforces the others, slowly weaving the separate threads of air, temperature, and liquid into the integrated fabric of a living world. Managing this emerging hydrosphere would require a global network of autonomous monitors, sensors floating on new lakes, embedded in riverbanks and orbiting above, all feeding data into climate models of unimaginable complexity. The engineers of this new Mars would become masters of a dynamic, growing system, learning to predict its storms, its droughts, and its currents. They would not just be building a world, but nurturing the first whispers of its weather, listening for the sound of the first rain falling on a plain that has waited billions of years to hear it. This final, living layer of the new atmosphere would be woven not by machines, but by life itself. While industrial arrays crack molecules with brute force, a more elegant and ancient technology waits in the wings, one that builds worlds through patience and self-replication. This is the frontier of synthetic biology, where we move beyond seeding simple algae and begin to design entire suites of dedicated terraforming organisms. Picture a lichen, but one engineered from its genetic foundations. Its fungal component could be armored with pigments to shield it from the still intense Martian ultraviolet radiation, while its algal partner diligently fixes atmospheric nitrogen, converting that scarce, inert gas into a usable form that enriches the soil. Beside it, a strain of bacteria could be designed with a singular purpose: to seek out and metabolize the toxic perchlorate salts that poison the Martian regolith, breaking them down and releasing harmless chloride or even a trickle of oxygen as a byproduct. These would not be solitary species, but a coordinated planetary microbiome, a living toolkit where each organism has a specific, programmed job in the grand environmental renovation. Deploying such a designed ecosystem would be an act of profound leverage. A single capsule of engineered spores, scattered by the wind or planted by rovers, could give rise to a self-sustaining colony that grows, reproduces, and spreads across the landscape for centuries. They would work autonomously, day and night, without needing a single watt of electricity from our reactors or a single command from mission control. In essence, we will be turning biology into the ultimate distributed technology, using self-replicating systems to perform the work of a million silent factories, softening the soil, adjusting the air, and preparing the ground for whatever comes next. The sheer efficiency of this approach is breathtaking, harnessing the same relentless drive for growth that transformed our own planet billions of years ago, but now with intention and direction. Yet, this power carries a responsibility of almost unimaginable weight. Introducing designed life onto a global scale introduces profound questions that transcend engineering. The first is biocontainment. What happens if a terraforming bacterium evolves in an unexpected way, or exchanges genes with a hardier, native extremophile we have not yet discovered? Could our carefully crafted nitrogen fixer mutate into a form that disrupts the very atmospheric balance we are trying to create? We are discussing the release of self-replicating code onto a planetary system with no off switch. The second question is one of legacy and ethics. We would be seeding an entire world with life that is entirely our creation, a permanent, living monument to our will. These organisms would become the foundation of a new biosphere, the ancestors to everything that might ever live on that future Mars. This shifts the project from a colossal construction job to an act of genesis, where every genetic decision we make today could echo for millions of years. It forces us to ask not just if we can build a breathable sky, but what kind of life we want to breathe within it, and whether we have the wisdom to design a world without becoming prisoners to our own creations. The silent factories and living terraformers all share a single, relentless master, energy. Without a torrent of power flowing ceaselessly across the planet, every mirror, every processor, every genetic tool we design is just a sculpture in the dust. The energy imperative is the non-negotiable foundation, a demand so vast it redefines what we mean by infrastructure. To grasp the scale, think of the total electrical power generated by every nation on Earth today. Now imagine needing to produce that same amount of energy on Mars, and then multiplying it by a factor of 10, or perhaps 100, to run the planetary scale industries of atmospheric creation for centuries. This is not about powering cities, it is about powering geology, about commanding the elemental forces that shape worlds. The machines that will crack carbon dioxide and bake oxygen from soil are not just energy hungry, they are energy obsessed, each one a gaping maw that must be fed around the clock for generations. So where could such a staggering flow of power possibly come from? The most visible answer is written across the Martian sky every day: sunlight. The concept is straightforward in theory: pave the deserts. Envision continent-sized fields of ultra-lightweight, self-cleaning solar panels, stretching from horizon to horizon, turning the weak red sunlight into a steady current. But the numbers are punishing. Mars receives less than half the solar energy Earth does, and each long, dusty night and global dust storm would plunge these fields into darkness and inefficiency. To compensate, we would need to cover an area larger than many countries just to match the output of a single large terrestrial power plant. The manufacturing, deployment, and maintenance of such a fragile, sprawling network becomes a logistical nightmare of its own, a permanent, planet-wide cleaning and repair operation fighting against the very environment it is trying to change. This leads many engineers to a more compact, relentless solution: nuclear fission. Instead of spreading energy collection across the landscape, we would concentrate it in thousands of advanced modular reactors. These would not be the colossal concrete towers of Earth, but sealed, autonomous units, perhaps buried for safety and stability. They could be placed anywhere, near the poles to melt ice, in the deep valleys to run chemical plants, providing steady, immense heat and electricity regardless of the time of day or the opacity of the sky. They offer the promise of density and reliability, but they impose a different kind of burden. Each reactor requires a constant supply of refined nuclear fuel, which means building an entire mining, processing, and waste management industry on Mars from scratch, another monumental sub-project hidden within the first. For some, even this is not the ultimate answer. They look to the future, to the dream of fusion power replicating the engine of the Sun in a contained reactor on the Martian surface. If it could ever be made practical and compact, fusion would be the holy grail, offering nearly limitless power from minimal fuel, perhaps sourced from the deuterium in Martian water ice. But we cannot build a civilization on a technology that has not yet left our laboratories. The terraforming project must begin with tools we understand or can realistically foresee. More speculative ideas push the infrastructure entirely off-world. Enormous solar power stations could be constructed in orbit around Mars, where sunlight is constant and unfiltered. These stations would convert solar energy into microwaves or lasers and beam it down to receiving stations on the surface, a clean river of power falling from the sky. Yet beaming such immense energy through the atmosphere we are trying to build raises questions of efficiency, safety, and potential climatic side effects we can scarcely model. The stark truth is that no single source will suffice. The energy backbone of a new Mars will necessarily be a hybrid monster, a patchwork of nuclear reactors humming at the poles, vast solar farms blanketing the equatorial deserts, and perhaps centuries later, the first experimental fusion plants coming online. This infrastructure cannot be an afterthought. it must be the very first thing we build, a silent, sprawling nervous system laid down before the muscles of industry can flex. It is the ultimate enabling technology, the difference between a dream and a world. And once this power begins to flow, it will illuminate the final, most human dimension of the entire endeavor, the cost. The new sky would be a chaotic, untamed force. Forging an atmosphere is only the beginning. The true challenge lies in teaching it how to behave. On Mars, with its longer day, dramatic axial tilt, and lack of vast oceans, the very physics of weather would be foreign. The global circulation patterns, the dance of high and low pressure, the birth of storms, all of it would unfold according to a rulebook we have never read. Our task shifts from creation to curation, from planetary alchemy to dynamic climate management on a scale that makes every hurricane and drought on Earth look like a minor local event. The goal is to nudge this alien weather toward a stable, temperate equilibrium, to prevent the colossal investment of our new atmosphere from collapsing back into a frozen state or spiraling into perpetual planet-engulfing dust storms. This is the art of atmospheric husbandry, where engineers become shepherds of an entire sky. Consider the simple fact of a Martian day, which is about 40 minutes longer than an Earth day. This slight difference, compounded over seasons and years, would subtly alter the Coriolis effect, the force that twists winds into great circulating systems. The storms on this new Mars might spin slower or cover wider areas, or persist for months longer than anything in our experience. Without large, temperature-moderating oceans to act as global heat sinks, continental interiors could swing between blistering daytime heat and deep, frigid nights, generating powerful and unpredictable winds. To guide this system, we might need to become landscape artists on a continental scale. One proposed method focuses on the planet's reflectivity, its albedo. The bright white polar ice caps act like a mirror, bouncing sunlight back into space and keeping the region cold. To encourage further warming and stabilize the climate, we could deliberately darken these areas. This could be done by spreading a thin layer of dark dust or sand over the ice, perhaps using automated vehicles, a process that would need constant renewal as winds shifted the material. It is a form of planetary makeup, changing the face of Mars to absorb more of the sun's warmth and lock in the greenhouse effect. More radical still are concepts for direct atmospheric steering. Imagine constructing vast, linear arrays of vertical structures, not buildings, but slender, networked towers stretching across thousands of kilometers of plains. These would act as artificial mountain ranges, designed to gently redirect prevailing wind patterns. By guiding where the warm and cold air masses flow, we could theoretically encourage stable weather bands and more predictable precipitation, preventing energy from building up into catastrophic superstorms. We might even seed specific clouds or manage humidity levels in key regions to ensure life-giving rain falls where the emerging biosphere needs it most, turning deserts into grasslands through deliberate, global irrigation from the sky itself. This level of control ventures into the realm of active, real-time planetary governance. It would require a nervous system of millions of sensors in the air, soil, and space, all feeding data into climate models of unimaginable complexity. Artificial intelligences would constantly analyze this flow, predicting system disruptions years or decades in advance and recommending tiny, corrective interventions. A release of aerosol here, a minor albedo adjustment there, to keep the entire vast breathing system in balance. The atmosphere becomes a living engine, and we are its mechanics, listening for every knock and murmur, understanding that stability is not a destination, but a continuous, delicate act of maintenance. This forever vigilance leads to the final, inescapable question, one that moves beyond physics and engineering into the realm of time, resources, and human will. The clock we build for Mars ticks in centuries, not years. The timeline for forging a breathable atmosphere is the most humbling dimension of all. Even with every technology we can dream of deployed at maximum scale, the process is measured in geological time. Optimistic computer models, assuming a relentless, perfectly coordinated global effort, suggest it might take 300 to 500 years just to achieve a thin, cold, but technically breathable atmosphere at the lowest points on the planet, like the bottom of the Hellas Basin. To reach a stable, Earth-like pressure and temperature that would allow liquid water to flow freely and forests to grow without enclosed domes, we are talking about 1,000 years, perhaps several thousand. This is not a mission with a ribbon-cutting ceremony at the end. It is a project that begins with our great-great-grandchildren and only truly finishes for people living in an era as distant from us as the Middle Ages are today. This staggering timescale transforms the entire endeavor. The challenge is no longer merely technical, it becomes profoundly human. It asks us to build something that cannot be finished in a single lifetime, to pour resources and genius into a sky we will never breathe. It demands a form of societal patience and purpose that has no precedent in our history. We are a species wired for immediate results, for quarterly reports and election cycles. Terraforming requires a civilization that thinks in chapters, where each generation sees itself as a caretaker, laying one more stone in a cathedral whose spire they will never see touch the clouds. The institutions needed to steward such a project would have to be designed for permanence and resilience beyond any corporation or nation-state that exists today. They would need to survive wars, economic collapses, and cultural shifts on Earth, maintaining focus on a goal whose payoff is always just over the horizon for the next generation. This is a test of narrative, of story. Can we craft a vision so compelling that it becomes embedded in our culture, taught to children for 100 generations, a North Star for our species? The project would need its own myths, its own heroes, and its own enduring symbols to keep the purpose alive long after the names of the original architects are forgotten. It becomes less about building an atmosphere and more about building a legacy, a single, unbroken thread of intention stretching across millennia. This perspective shifts the meaning of every robotic factory and every engineered microbe. They are not just tools, they are messages in a bottle we are sending to our own future. We are designing machines and organisms that must operate, adapt, and sustain themselves long after the manuals have turned to dust and the control rooms have been repurposed. The software guiding them would need to be inherently self-correcting and stable, capable of evolving its strategies without losing its core purpose. The biology we introduce would need to be robust enough to thrive through climatic swings we cannot predict, becoming a permanent, self-sustaining part of the new world's fabric. In this light, the energy reactors and the orbital mirrors are not just infrastructure, they are monuments to patience. They are the pyramids of a scientific age, built not for a pharaoh's afterlife, but for humanity's future life. The psychological adjustment is immense. It requires us to find meaning not in completion, but in contribution. The engineer who designs a soil processor that will run for 500 years must derive satisfaction from knowing she has added a single, vital sentence to a story that will take 1,000 years to tell. This generational mindset is perhaps the rarest resource of all, more scarce than any nitrogen deposit or nuclear fuel. Cultivating it may be the ultimate innovation, the social technology without which all the physical engineering is merely a very expensive gesture. The most profound obstacle may not be gravity or chemistry, but a simple question of conscience. Before we ever warm a single polar cap or release a single engineered microbe, we must confront an ethical dilemma that transcends engineering. Do we, as a species still learning to care for our own world, possess the inherent right to fundamentally reshape another? This is not a debate for the distant future. It is a practical consideration that will shape international treaties, mission designs, and funding decisions long before the first terraforming reactor is ever powered on. The core of this dilemma rests on two immense possibilities, each carrying its own weight. The first is the potential for native Martian life. Our probes have found tantalizing hints of liquid water in the past and complex organic molecules in the present. While we have seen no definitive proof of life, we have also not explored more than a tiny fraction of the planet, especially its deep subsurface aquifers. It is entirely possible that Mars harbors its own unique, microscopic biosphere, clinging to existence in briny pockets beneath the soil. A full-scale terraforming project, with its radical shifts in temperature, chemistry, and radiation levels, would almost certainly overwhelm and extinguish these fragile native organisms if they exist. We would be committing, however unintentionally, an act of planetary-scale biocide, erasing a second genesis of life in the solar system before we even understood it. This forces us to ask what value we place on life that is not our own, life that is alien in every sense of the word. Is its right to exist in its own strange, quiet way greater than our desire to expand our own? The second possibility is that Mars is truly, utterly sterile. Even in this case, the planet is not a blank slate. It is a pristine museum, a 4-billion-year-old archive of solar system history. Its untouched craters, layered sediment, and unweathered geology hold a continuous record of cosmic events, climatic shifts, and planetary formation that has been erased by Earth's active geology and biosphere. By flooding it with a new atmosphere and a new water cycle, we would be pouring water over the most important pages of that archive, blurring the ink of cosmic history forever. The scientific loss would be permanent, a sacrifice of pure knowledge for the sake of habitation. These concerns give rise to competing ethical frameworks, each with its own compelling logic. One view is the planetary park model. It argues that Mars, like a wilderness preserve or a World Heritage Site, has intrinsic value in its current state. Its stark beauty, its scientific record, and its potential as a sanctuary for native life grant it a right to remain unaltered. Our role under this view is one of careful stewards and observers, exploring with a light touch and preserving its otherworldly nature for all future generations to study and appreciate. We would live in enclosed habitats, visitors in a grand cosmic museum. The opposing view is often called the cosmic imperative. It holds that life, especially conscious, intelligent life, has a fundamental duty to spread, grow, and flourish. In this vast, silent universe, a dead rock represents a tragic waste of potential. Our ethical obligation, therefore, is to awaken barren worlds, to turn them into cradles for new ecosystems and new civilizations. Mars is not a museum under this philosophy. It is a seed, and we are the gardeners with a responsibility to help it bloom. These are not abstract academic debates. They are the foundations upon which laws will be written. A global consensus, likely enforced by international treaty, would need to establish rigorous planetary protection protocols. Before any atmospheric alteration could begin, a comprehensive, definitive search for native life would be mandatory, requiring probes to drill deep, sample widely, and analyze with tools we have not yet invented. The discovery of even a single living Martian microbe could halt the entire terraforming project for centuries, or redirect it toward creating protected microbial reserves under vast, transparent domes. The ethics extend to our own creations as well. If we seed Mars with our engineered terraforming organisms, we are making a permanent choice. That life will become part of the planet's future, evolving in ways we cannot predict. We must accept responsibility not just for building that new biosphere, but for every consequence that flows from it for all time. This ethical layer adds a deep complexity to the already staggering technical challenge. It means the first and most important machine we send to Mars may not be a reactor or a mirror, but a microscope of unprecedented sensitivity, And the most vital blueprint may not be for a factory, but for a covenant, a promise we make to a world and to our own future about what kind of universe we want to build. The price tag for a new sky is a number that does not yet exist in our mathematics. We can calculate the energy, the mass, the machinery, but translating that into dollars, euros, or yuan is an exercise in absurdity. The cost is, for all practical purposes, infinite within the framework of any economy that exists on Earth today. No single nation, no consortium of corporations, no existing budget could bear it. This forces a staggering realization: the terraforming of Mars is not just an engineering project, it is the blueprint for an entirely new economic reality. It demands what thinkers call a post-scarcity society, one where the fundamental needs of life are met for all, freeing the collective productive capacity of civilization to take on generational tasks of cosmic scale. Alternatively, it requires the invention of a truly interplanetary economy, where value is measured not in terrestrial currency, but in energy credits, computational cycles, or kilograms of atmospheric gas produced. The very act of building the sky would create its own currency, its own market, and its own logic of value. This leads to the most pressing political question of all: who owns the process? Who has the authority to decide the atmospheric recipe, to set the warming timeline, to choose which valleys flood and which deserts bloom? The governance of a planet is a power unlike any other. Would this be a project of a unified Earth government, a fragile dream of global cooperation made real by a shared off-world destiny? Or would it fall to a corporate consortium, a coalition of the wealthiest entities in human history, who fund the venture in exchange for exclusive rights to the new world's resources, effectively becoming landlords of an entire biosphere? There is a third, perhaps inevitable possibility. The first generations of Martian settlers, the engineers and scientists living in pressurized domes and managing the global machinery, would over time develop their own culture, their own interests, and their own claim to the world they are physically building. Long before the air is breathable, a movement for Martian independence could arise. These builders might declare that those who labor to create the sky have a right to govern it, leading to a profound political separation from an Earth they may see as a distant, interfering shareholder. The politics of planetary engineering are therefore inseparable from the physics. Control over the climate-altering technologies, the orbital mirrors, the super greenhouse gas factories, and the genetic libraries of terraforming organisms represents ultimate power. It is the power to make a world habitable or to withhold that habitability. This creates a terrifying potential for conflict, a new form of geopolitics played out not with borders on a map, but with atmospheric pressure gradients and solar reflection coefficients. A dispute over resource rights could escalate into a form of environmental warfare, where one faction threatens to collapse the nascent climate if their demands are not met. The governance structure for this endeavor must be as robust and fault-tolerant as the reactors powering it. It would need mechanisms for resolving disputes across generations, for incorporating new scientific understanding, and for representing the interests of those not yet born who will inherit the world being made. It may require a new branch of interstellar law, founded on principles of planetary stewardship rather than territorial ownership. The dream of a breathable Martian sky ultimately holds up a mirror to our own world, asking if we can achieve the unity, the patience, and the wisdom here on Earth to even begin such a project there. Every blueprint for a new sky must also include an emergency exit. Engineering a planetary climate is an act of profound hubris, precisely because the systems we are trying to manipulate are unimaginably complex and have no precedent. Our models, built from a single data point, Earth, would be attempting to predict the behavior of an entirely alien atmosphere under stresses it has never experienced. The greatest danger is not that we fail to warm Mars, but that we succeed too well, triggering a runaway greenhouse effect we cannot stop. Imagine if the cascading release of carbon dioxide from the poles and soil, amplified by our super greenhouse gases, crossed a tipping point. The temperature could climb relentlessly, boiling away any new oceans before they fully form, baking the landscape and pushing the atmosphere toward a thick, crushing, Venus-like state. What began as a project to create a garden could end by forging a pressure cooker, permanently locking the world in a state worse than its original frozen silence. This is the nightmare scenario that haunts every climate model, a reminder that planetary engineering is a one-way street with no U-turns, but a runaway greenhouse is only the most dramatic of many potential failures. The chemical interactions in a newly forged atmosphere are a vast, unknown equation. What if the gases we release, under the influence of intense ultraviolet radiation or novel catalytic dust in the Martian soil, combine to form persistent toxic compounds? We might fill the sky only to discover it is laced with a slow-acting poison, or with an aerosol that blocks too much sunlight, plunging the planet into an artificial ice age. The biological tools we introduce carry their own unique perils. An engineered terraforming microbe designed to be robust could acquire a random mutation or exchange genes with a hardier native extremophile we never detected. This new hybrid organism might no longer produce oxygen as intended, but instead start metabolizing the very atmospheric buffers we are trying to build, or worse, it could become an invasive plague, outcompeting all other life and collapsing the fledgling ecosystem from within. These are not bugs in a software program, they are self-replicating errors in the genetic code of a world, and once released, they cannot be recalled. This inherent unpredictability forces a radical shift in engineering philosophy. On Earth, we build bridges and test them to destruction. We prototype engines in controlled labs. For terraforming, there is no small-scale test. You cannot run a trial atmosphere on a continent-sized plot. Every intervention is the real thing, a global experiment from the very first day. Therefore, the entire process must be designed from the ground up with contingency and control woven into its fabric. This means building in what engineers call off switches, fail-safes that can slow or reverse a process gone awry. One concept involves having the capability to rapidly deploy sun-blocking aerosols into the upper atmosphere, a global dimmer switch to cool a runaway warming trend. Another is to design the chemical processes so they can run in reverse, pulling specific problematic gases back out of the air and sequestering them back into stable mineral forms. The genetic tools we use might be designed with built-in biological limits, perhaps requiring a synthetic nutrient we control to survive, giving us a kill switch should they evolve beyond their programming. Ultimately, risk mitigation becomes the central pillar of the entire endeavor, more important than any single technology. It means proceeding with a humility that matches our ambition, advancing in the smallest possible incremental steps, monitored by a global nervous system of sensors that feeds data into ever-evolving predictive models. It means having the courage to pause or even to step back if the system behaves in an unexpected way, even if that delay spans decades. The stakes are not a failed mission or a lost investment. They are the entire future potential of a world. To forge a new sky is to accept a permanent duty of care, a vow to watch over the breathing giant we awaken, listening always for the first sign of a fever we cannot cure. This forever vigilance is the true cost of playing with the forces that shape planets, and it asks if we are wise enough to be guardians before we dare to be creators. The first breath of free Martian air is a promise written in centuries, not years. For the people who will actually build this new sky, life will unfold within a paradox, dwelling in sealed sanctuaries while the world outside is slowly, meticulously remade. This is the interim habitat paradigm, a civilization in waiting, living in a permanent state of becoming. For generations, human existence on Mars will be defined not by open plains, but by the inside of a dome, the curve of a pressurized tunnel, or the vaulted ceiling of a lava tube city. These are not temporary camps, but self-sustaining arcologies, miniature Earths carved into the alien soil, representing a parallel engineering track every bit as complex as atmospheric generation. Their primary mission is stark survival, maintaining a perfect closed-loop bubble of biology where every drop of water, every molecule of oxygen, and every scrap of organic waste is tracked, purified, and relentlessly recycled. The technology for this is a non-negotiable prerequisite, the lifeboat that keeps civilization alive until the planet itself is ready to embrace it. Within these enclosed worlds, the rhythm of life would be profoundly shaped by the grand project outside. Children would be raised with two sets of environmental data. One is the habitat's vital signs, the constant hum of air recyclers and water purifiers that keep their immediate world alive. The other, more abstract but infinitely more hopeful, would be the planetary vital signs. They would not check for rain or sunshine, but for parts per million increases in atmospheric oxygen, for incremental rises in global average temperature, and for the slow growth of total atmospheric pressure. These would be their weather reports, charting the progress of a storm system of creation that moves with glacial patience. A milestone like the average pressure reaching 10% of Earth's would be a global holiday, a celebration of a threshold crossed in a journey of 1,000 steps. This waiting society would develop a unique relationship with the outside. The first settlers venture out only in fully pressurized suits, bulky armor against a near vacuum. But as the decades pass, those suits become progressively less cumbersome. The day a new, lighter model is issued, one that relies on the slightly thicker air to reduce the pressure differential, is a day of liberation. It means the outside world is becoming slightly more accessible, the barrier between human and planet growing a little thinner. Eventually, perhaps after a few hundred years, settlers might step into an area with only a breathing mask and a heavy coat, feeling the actual pressure of the Martian atmosphere on their skin for the first time, a tangible taste of the future. This gradual transition would reshape psychology itself. How does it feel to watch your own sky being constructed? To know that the pinkish haze outside your dome is not a natural given, but a work in progress, a chemical canvas upon which your descendants will paint a blue. It fosters a mindset of both profound patience and direct agency, where every individual's work, from maintaining algae vats to repairing soil processes, is a direct contribution to the literal horizon. The arcologies themselves are marvels of microengineering. To sustain thousands of people for centuries without resupply from Earth, they must achieve near-perfect resource closure. Vast underground aquaponic farms, lit by tailored spectra of LED light, would produce food while simultaneously reprocessing carbon dioxide and organic waste. Every exhaled breath is captured, its carbon extracted and fed back to the plants, its moisture condensed and returned to the drinking water cycle. Radiation shielding, perhaps provided by meters of regolith overhead or by ingenious layers of water-filled walls, is a constant design priority, protecting the fragile genetic material within both the human residents and the cultivated ecosystems that sustain them. These habitats are more than cities. They are living organisms in their own right, fragile bubbles of Earth life beating in the heart of an alien world. Their sustained success is the quiet, unsung foundation that makes the noisy, centuries-long project of atmospheric forging not just a scientific endeavor, but a human story. They are the keepers of the flame, ensuring that when the new sky is finally ready, there will be someone there to look up and breathe it in. The sky is a construction project, and you are born inside the scaffolding. For generations, the only reality for a Martian is this duality, a life split between the intimate, recycled air of the habitat and the colossal, unfinished world being assembled beyond the dome. This psychological landscape is perhaps the most complex environment we would ever need to engineer. How does a civilization maintain its purpose when the ultimate goal lies centuries beyond any individual's horizon? The answer would reshape human culture at its core, forging an ethos unlike any in our history. A society dedicated to terraforming would need to find meaning not in completion, but in contribution. Your life's work might be to maintain a single chemical processor array that will not finish its task for another 200 years. Your art might celebrate not a sunset, but a graph showing a steady, century-long rise in atmospheric pressure. Your stories would not be about heroes who accomplish great deeds in a lifetime, but about ancestors who laid a single stone in a path their descendants will walk. This generational mindset cultivates a profound form of patience, a kind of temporal humility. Success is measured in incremental, collective gains so small they are invisible day to day, but monumental across generations. It redefines legacy, making every individual a vital link in a chain of effort stretching into a future they can only imagine. This could foster an incredible sense of unity and shared destiny, a cultural immune system against the short-term thinking and factionalism that often plague societies on Earth. The project itself becomes the central pillar of identity, a common story so powerful it binds people together across centuries. Yet, this long horizon also carries profound psychological risks. The sheer scale of time could become a source of existential weight. For some, the knowledge that they will never walk under an open sky, never feel natural rain, might lead to a sense of disconnection or quiet despair. Could a human spirit thrive in a perpetual state of becoming, always a visitor in a home that is never quite finished? This tension might give rise to countercultures or movements of rebellion, not against leaders, but against the timeline itself. Some might advocate for risky technological shortcuts, pushing for faster change regardless of the danger. Others might retreat entirely into virtual realities or art forms that simulate a completed world, a form of cultural escapism from the slow march of progress. Managing this human element becomes a critical engineering constraint. Project leaders would need to design not just machines, but experiences that make the long-term tangible and rewarding. Education would focus on systems thinking and deep time, helping children visualize their place in the multi-generational story. Regular, meaningful milestones would be celebrated with the fervor of national holidays, the first rainfall in a new sea basin, the day the average temperature climbs above freezing for an entire Martian year. These events transform abstract data into shared sensory memory, a promise that the work is real and the future is drawing nearer. The arts would evolve to mirror this unique existence. Music might incorporate the low hum of atmospheric processes. Literature might explore the inner lives of those who care for machines that will outlive them by millennia. Architecture within the habitats would likely feature vast windows and transparent domes, not just for light, but to keep the unfinished sky constantly in view, a reminder of the purpose that structures every day. This constant visibility of the project turns the environment itself into a narrative, a living epic written in chemistry and climate. Ultimately, the mental landscape of the terraformer may represent a new chapter in human consciousness. It is a perspective that balances deep patience with unwavering agency, finding profound purpose in a foundation you will never see completed. It asks us if we can learn to be gardeners of time, planting forests we will never sit under, for the sake of a shade we can only believe in. This human need for meaning within a lifespan is not a sidebar to the engineering. It is the gravity that holds the entire endeavor together, the invisible force that will determine whether the dream of a blue Mars lives in the human heart long enough to become real in the sky. The relentless innovation demanded by Mars could revolutionize life on Earth. The technologies we invent to build a sky on a dead world are not one-way tools. They are blueprints for solving our most pressing problems right here at home. This creates a powerful feedback loop where the grandest vision imaginable becomes a catalyst for immediate, tangible progress, spinning off solutions that could reshape our own planet long before the first tree takes root on Martian soil. The most direct application lies in the very systems that will keep settlers alive for centuries. To survive on Mars, we must master closed-loop life support with near-perfect efficiency, recycling every drop of water, every molecule of oxygen, and every scrap of organic waste. The biological and mechanical systems developed for this are not just for space. Imagine transplanting that same technology into our terrestrial cities. Ultra-efficient atmospheric processors and water reclamation units could transform urban infrastructure, turning megacities into self-sustaining ecosystems that drastically reduce their demand on freshwater sources and eliminate waste. Buildings could be designed as miniature arks, managing their own climate and resources with Martian-grade precision, slashing energy use and creating a new standard of sustainable living. This is not a distant dream, it is a direct engineering pathway from a Martian habitat to an Earth-based arcology. The same principle applies to the air itself. On Mars, we will build machines to crack carbon dioxide and release oxygen. On Earth, we face the opposite but related crisis, an overabundance of carbon dioxide destabilizing our climate. The advanced solid oxide electrolysis cells and catalytic processors designed for Martian air could be scaled and adapted into a new generation of carbon capture technology. These would not be the energy-intensive prototypes of today, but highly efficient, industrialized systems born from the necessity of processing an entire planet's atmosphere. They could be deployed at power plants, integrated into manufacturing, or even form the basis of large-scale direct air capture facilities, actively scrubbing greenhouse gases from our own sky and turning a liability into a resource, perhaps by converting the captured carbon into stable building materials or synthetic fuels. The harsh Martian environment will also force a revolution in materials science. To shield habitats from radiation and withstand extreme temperature swings, we will need new composites, smart polymers, and self-healing ceramics. These materials, born from extraterrestrial necessity, will inevitably migrate back to Earth. They could lead to ultra-durable, energy-efficient building materials for disaster-resilient housing, new medical shielding for radiation therapy, or lightweight, super-strong alloys for transportation and renewable energy infrastructure, like wind turbine blades that last for decades in harsh marine environments. Perhaps the most transformative spin-off of all will be in energy. The Terraforming project's insatiable appetite for power will drive breakthroughs in solar cell efficiency, compact nuclear fission, and perhaps even the first practical fusion reactors. The energy systems developed to light a new world could, in turn, illuminate our own, providing the foundation for a truly post-scarcity society on Earth. Abundant, clean energy solves a multitude of interconnected problems, from desalinating seawater for agriculture to powering the recycling of all our material goods. In this way, the Martian project acts as a forcing function, a monumental challenge that compresses a century of energy research into a few desperate decades. This creates a virtuous cycle that justifies the staggering investment. Each spin-off technology developed for Mars can be commercialized on Earth, generating economic value, funding further research, and building public support by demonstrating concrete benefits in the here and now. The pursuit of a second home becomes the engine for healing and advancing our first one. The project transcends mere exploration. It becomes a grand societal project with dividends paid across generations and across planets. proving that the greatest journeys outward often lead to the most profound improvements inward. The silent, sprawling work of building a sky will be performed by minds of silicon and steel. This centuries-long symphony of chemical reactions, energy flows, and climate adjustments is too vast, too complex, and too dangerous for human hands to conduct in person. The true architects and laborers of a new Mars will be armies of autonomous machines, directed by an artificial intelligence of a kind we have not yet created, a mind capable of thinking on a planetary scale. This is not a supporting technology, it is the central nervous system of the entire endeavor, the prerequisite that makes every other step possible. Imagine not a single robot, but a global ecology of specialized machines, each a cell in a larger, thinking organism. Solar-powered excavators that crawl across the night side of the planet, mining regolith without a single operator. Aerial drones that ride the thin winds, sampling atmospheric composition and mapping ice melt. Subsurface probes that navigate through aquifers, monitoring water flow and soil chemistry. These are not remote-controlled toys, they are independent agents, making millions of local decisions per second to fulfill a global objective set by their overseeing intelligence. They must be resilient beyond anything we build today, capable of operating for decades in abrasive dust, extreme cold, and relentless radiation, repairing themselves and each other, and adapting their strategies when the unpredictable Martian environment throws them a curveball. The scale of coordination is the true challenge. A single factory producing super greenhouse gases must be perfectly synced with the orbital mirrors adjusting their angle, the soil processors in a different hemisphere ramping up oxygen production, and the network of sensors detecting a nascent dust storm that could disrupt it all. This is a dance with billions of moving parts, a logistical problem that would overwhelm any team of human planners. Only a super-intelligent AI, a system capable of real-time global optimization, could hold the entire model in its mind and make the micro-adjustments needed to keep the project on track. This AI would become the steward of the climate itself. It would ingest a constant flood of data from every sensor on and above the planet, running hyper-advanced climate simulations that predict the outcome of every possible intervention. Should we darken the northern polar cap by 5% this decade? What is the precise optimal release rate for nitrogen from the southern soil processes to balance the new oxygen without triggering unstable atmospheric chemistry? The AI would run these scenarios not as a one-time calculation, but as a continuous living forecast, updating its models with every new data point and refining its commands to the machine networks below. It would be a form of weather control, but born from deep learning and predictive analytics rather than myth. Developing this level of artificial intelligence is itself a monumental frontier. It pushes beyond today's machine learning into realms of true reasoning, long-term strategic planning, and robust common sense. This AI must understand not just data, but context and consequence. It must be trustworthy, its goals perfectly aligned with the long-term vision of a stable, breathable Mars, and its decision-making processes transparent enough for its human partners to understand and, if necessary, override. We are talking about creating a new form of consciousness, one born not for conversation or creativity, but for caretaking on a geological scale. Its mind would be shaped by the rhythms of a world, thinking in seasons and centuries, its success measured in the slow, steady climb of an atmospheric pressure graph. In this light, the terraforming of Mars may be the crucible that forges the first true planetary intelligence. We would not be building a tool, but a partner in world building, an entity whose very purpose is to nurture a biosphere into existence. This raises a profound and final question about the legacy of such a project. When the sky is finally blue and the air is finally sweet, who or what will truly be the guardian of this new world? The most fragile part of our new sky would be its own existence. all the trillions of tons of gas we painstakingly release would remain under a constant, invisible siege from the solar wind, that relentless stream of charged particles blowing from the sun. Without a solution, the atmosphere we build over centuries could be slowly stripped away over millennia, a heartbreaking reversal of all our work. This vulnerability forces a radical defense, one that moves engineering from the planetary surface to the space around it. The most ambitious answer is not to thicken the air, but to build a shield for it, a global magnetic umbrella known as the Magnetic Shield Megaproject. This concept centers on a single, staggering piece of infrastructure placed at a precise point of celestial balance. Between Mars and the Sun lies a location called the Sun-Mars L1 Lagrange point, where the gravitational pulls of the two bodies and the centrifugal force of an object's orbit perfectly cancel out. Here, a satellite can hold a fixed position relative to Mars, forever between the planet and its star. At this strategic vantage, we would construct not a telescope or a communications relay, but a colossal magnetic field generator. Its sole purpose would be to create an artificial magnetosphere, a protective bubble large enough to envelop the entire planet in its embrace. The engineering of such a device defies simple analogy. It would likely take the form of a massive loop or coil, potentially kilometers in diameter, made from superconducting materials. In the deep cold of space, these materials could carry immense electrical currents with virtually no resistance, generating a powerful, stable magnetic field without the crippling energy loss you would experience on Earth. This field would be a dipole shaped like the one surrounding our own planet, with magnetic lines arching out into space. When the charged particles of the solar wind encounter this magnetic barrier, they would be deflected, flowing around the bubble like water around a stone in a stream. Mars would sit in the calm wake, its atmosphere shielded from the erosive force that has scoured it for eons. The scale of power required is, as with every aspect of this project, astronomical. The shield generator would need a continuous and immense supply of electricity to maintain its field. This power could be beamed from colossal solar arrays dedicated to the task, or perhaps from a compact, high-output nuclear fusion reactor, if such technology becomes viable. The structure itself would be a masterpiece of materials science, engineered to withstand micrometeoroid impacts, thermal extremes, and the intense stresses of generating such a powerful field. It would have no moving parts, yet it would be one of the most dynamic and vital machines ever conceived, a silent sentinel holding a vigil over a world. If successful, the effects would be transformative. By drastically reducing atmospheric sputtering, the shield would change the fundamental equation of terraforming. It would turn Mars from a leaky vessel into a sealed container. The gases we produce would accumulate more efficiently, and crucially, they would stay. This makes the entire centuries-long effort sustainable over geological time, ensuring that a breathable sky, once achieved, becomes a permanent feature of the planet. The shield would not create the atmosphere, but it would allow our creation to endure, shifting the project from a temporary intervention into a lasting legacy. This structure stands as perhaps the definitive megastructure, a pure symbol of our species' aspiration to not just visit worlds, but to care for them. It represents a shift from conquest to stewardship, from altering a landscape to safeguarding a biosphere. It is a declaration that we understand the forces that shape planets, and that we have learned enough to gently counter them. The magnetic shield would be invisible to a future settler standing on the surface, feeling a breeze from a protected sky. Yet its presence would be felt in every breath, the ultimate monument to foresight, built not on the ground, but woven into the fabric of space itself, a guardian whose only function is to allow a world to live. There exists a shortcut so violent it redefines the meaning of planetary engineering. Instead of patiently coaxing gases from the soil over centuries, we could steal an entire sky from the depths of the solar system and hurl it at Mars. This is the asteroid and comet redirect strategy, a concept that trades subtlety for staggering cosmic force. The raw materials we need, water, ammonia, and other volatiles, are not scarce, they are simply in the wrong place. The outer solar system is a deep freezer filled with icy wanderers, pristine remnants from the dawn of our planetary system. A single, carefully selected comet could contain more water than all the lakes on Earth, and its frozen heart would be rich in ammonia, a compound of nitrogen and hydrogen. The theory is brutally straightforward. Nudge one of these primordial icebergs onto a collision course with the red planet. The kinetic energy of an object miles across striking at tens of thousands of miles per hour would be beyond comprehension. Upon impact, it would not merely crash, it would detonate, vaporizing itself and a vast crater of Martian crust in an instant of apocalyptic fury. That cataclysm, however, is the point. The titanic release of energy would flash heat millions of tons of ice directly into water vapor and gases, injecting them violently into the atmosphere in one single, dramatic pulse. The impact itself would also deliver a massive shock of heat to the planet's crust, a global fever that could accelerate the release of other trapped volatiles from the soil. In one spectacular event, you could theoretically accomplish what might take a network of factories 100 years, adding both mass and warmth to the fledgling sky in a geological heartbeat. It is the ultimate shortcut, the definition of high risk, high reward. But the risks are not just high, they are existential. An impact large enough to meaningfully alter a planetary atmosphere would be a world-shaking event, literally. The seismic waves would circle the globe, potentially triggering volcanic activity in long dormant regions and reshaping the very geology we would be trying to inhabit. The immediate aftermath would see a towering plume of dust and debris ejected high into the atmosphere, enveloping the entire planet in a shroud that could block sunlight for years or even decades. This artificial nuclear winter would plunge temperatures, freezing out any new water vapor and potentially halting all other terraforming progress dead in its tracks. We might trade a century of careful work for a millennium of deeper cold. Furthermore, the chemistry of these distant bodies is not perfectly pure. Alongside the water and ammonia, a redirected comet could deliver a cocktail of toxic cyanide compounds or other complex organics that would poison the young atmosphere we are trying to create. It is a gamble of almost unimaginable scale where the price of failure is not a lost probe, but a permanently scarred and potentially uninhabitable world. This audacious idea serves as a stark boundary marker on the spectrum of approaches. On one end lies the patient, meticulous work of in situ resource utilization, the slow alchemy of building a sky molecule by molecule from the planet itself. On the far other end lies this cosmic cannonball approach, a single roll of the dice with a planetary biosphere as the stakes. It highlights a fundamental tension in the human spirit when faced with a task of such monumental patience, the eternal temptation of the quick fix, the overwhelming desire to see a blue sky in our own lifetime, even if the method to achieve it risks everything. The very fact that such a strategy is seriously contemplated tells us less about its practicality and more about the psychological weight of a 1,000-year timeline and the breathtaking audacity required to even think on such a scale. The final act of building a sky is not about creation but about subtraction. After centuries of effort, a thick, warm atmosphere blankets Mars, rich with the oxygen we need. Yet this triumph contains the seeds of a new crisis. The very carbon dioxide that served as the greenhouse foundation for this new world now lingers in overwhelming excess. Left unchecked, it would push the climate into a permanent, scorching fever and turn any nascent oceans into a corrosive, acidic bath, poisoning the waters before complex life could ever gain a foothold. The solution to this paradox lies in a process as old as Earth itself, the slow, patient work of turning air into stone. This is the Carbonate Solution, the planetary scale art of locking away a sky we spent ages building. To understand this, look at our own planet. The white cliffs of Dover, the vast limestone aquifers beneath continents, even the shells on a beach, these are all forms of carbonate rock. They are Earth's long-term carbon vaults, the result of carbon dioxide from the ancient atmosphere dissolving in water and reacting with minerals, eventually precipitating out as solid rock. On a terraformed Mars, we would need to accelerate this geological cycle from millions of years to mere centuries, becoming deliberate architects of the planet's very crust. The goal is to draw down the excess carbon dioxide from the air, stabilizing the climate at a temperate equilibrium and clearing the chemical stage for a truly balanced biosphere. One path leverages the biology we have already introduced. Specially engineered microbes or simple marine organisms could be designed to thrive in the new Martian seas. As they metabolize minerals and dissolved carbon dioxide, they would form microscopic carbonate shells or excrete carbonate compounds. When these organisms pass on, their tiny shells would rain down to the ocean floor, accumulating over generations into thick layers of sediment that, under pressure, would eventually become limestone. We would be farming rock, using self-replicating life to slowly, gently filter the sky and lay down the bedrock of a new world. It is a beautifully elegant form of natural engineering where the problem becomes part of the landscape. For a faster, more controlled process, we would turn to industrial chemistry. Imagine networks of pipelines snaking from atmospheric processing plants to deep geological basins. Here, advanced facilities would compress the captured carbon dioxide into a supercritical fluid, a dense, liquid-like state. This fluid would then be injected under high pressure into porous rock formations deep underground, such as ancient basalt layers. Once there, a remarkable chemical reaction begins. The carbon dioxide reacts with minerals in the basalt, like calcium and magnesium, to form solid carbonate minerals, essentially growing permanent, stable rock within the pores of the existing stone. It is mineralization, a process that securely binds the carbon away for millions of years. This method turns the subsurface of Mars into a permanent carbon landfill, a geological tomb for the gaseous remains of the old, dead world. This deliberate capture phase reveals the ultimate truth of planetary engineering. Terraforming is not a linear path from dead to alive. It is a dynamic, cyclical dance of release and restraint. We must first liberate gases on a colossal scale to warm and thicken the atmosphere, and then, with equal precision, we must recapture a significant portion of them to fine-tune the climate and ensure its long-term stability. It is a demonstration of profound balance, moving from brute force creation to delicate, ongoing stewardship. The project matures from building an atmosphere to managing a complex geochemical system, where every action has an equal and opposite reaction that must be planned for centuries in advance. The Carbonate Solution, whether biological or industrial, represents this mature phase where we learn to put parts of the sky back into the ground, completing the cycle and finally achieving a world that can maintain itself. This final, quiet act of burial is what makes the vibrant, living world above it possible. Centuries of labor culminate in a single, silent gesture. In a broad valley basin where the atmospheric pressure has finally crept high enough, a person stands surrounded by the hum of machinery and the held breath of history. They are not an explorer in the classic sense, but a descendant of the builders, born under dome lights to parents who monitored oxygen graphs. Their suit is a lighter model than those of the first settlers, a testament to the thickening sky outside. A medical team waits nearby, sensors ready, but the moment belongs to them alone. With deliberate care, they reach up, release the seals, and lift the helmet from their head. The first sensation is not of air, but of absence, the sudden quiet after the constant whisper of the suit's recyclers. Then the cold, a thin, sharp chill against the skin, carrying the faint, metallic scent of rust and ozone. The air is desperately thin, perhaps equivalent to the peak of Earth's highest mountain, and they must still wear a small nasal cannula feeding supplemental oxygen. But they are breathing it. Their lungs draw in the outside Martian atmosphere, a mixture painstakingly forged from polar ice and baked soil, and they do not fall. This is the final test, and it passes. The act is more symbolic than practical, yet its meaning vibrates through the very foundations of the endeavor. For generations, the project existed as data streams and engineering reports, a colossal abstraction measured in percentages and partial pressures. In this one vulnerable human breath, it becomes real. Mars is no longer an absolute adversary, a place where a suit breach means instant, violent loss. It has become a place of gradients, of hardship that can be endured, of an environment that has been nudged, however slightly, toward accommodation. The psychological shift is monumental. The settlers are no longer just custodians of a machine that makes air. They are the first inhabitants of a world that is learning to hold them. This transforms their relationship with the planet from one of opposition to one of nascent belonging. The outside is no longer purely a lethal workspace to be endured in armor, but a frontier that is slowly, irrevocably opening. This milestone, however, is a beginning, not an end. The celebratory images of that first unassisted breath would show a person still bundled, still reliant on auxiliary oxygen, standing on a landscape that remains barren and red. It underscores the long road still ahead. The atmosphere at this stage is a fragile, early draft. Storms could still arise that would force everyone back into full suits for months. The chemical balance is delicate, requiring constant vigilance from the global network of our stewards and machines. Yet, the direction of the arrow is now undeniable. Every generation after this one will breathe a little easier, require a little less assistance, and see a little more green tinting the edges of their world. That first breath is the turning of a key in a lock that took 1,000 years to forge, opening a door to a future where humanity is no longer a visitor in a dome, but a species living under its own made sky. That first breathable air marks the beginning of a deeper responsibility. The monumental task of forging a new sky does not conclude with a celebration, it simply changes form. The work evolves from planetary engineering into a permanent, delicate practice of planetary stewardship, managing the climate of a terraformed Mars, its emerging weather patterns, its engineered ecosystems, and its intricate geochemical cycles becomes a non-negotiable, ongoing duty for every generation that follows. This new world would not be a wild, self-regulating planet like Earth. It would be a profoundly fragile, human-made artifact, a garden on a global scale that requires constant, vigilant care. The atmospheric processors and orbital mirrors do not get powered down. They become part of a permanent life support system for an entire biosphere. This raises a profound and humbling question about our ultimate role. Are we merely visitors who built a habitat, or have we become gardeners of an entire planet, responsible for every storm, every season, and every breath of life within it? The precedent set here would echo for eternity. Every decision, from the genetic code of a terraforming microbe to the long-term management of atmospheric gases, establishes a template for how our species interacts with other worlds. If we can learn to nurture this one fragile, constructed environment, we take the first real step toward a future where humanity is not just a resident of planets, but a conscientious shaper of them. This transforms the legacy of the project's engineers. Their greatest achievement is not merely the blue sky or the flowing water. It is the birth of an entirely new branch of knowledge, planetary systems management. This discipline would fuse climate science, ecology, systems engineering, and ethics into a single framework for caring for a world. It is the operating manual for a living planet, written in real time by those who must keep it alive. The practitioners of this new science would be the planet's physicians, listening to its vital signs through millions of sensors, diagnosing imbalances years before they become crises, and prescribing tiny, precise interventions. A slight adjustment to an orbital mirror's angle, a carefully timed release of a cooling aerosol, the introduction of a new soil bacterium to fix a nutrient imbalance. Their tools are climate models of unimaginable complexity, and their canvas is the entire sky. This forever vigilance redefines what it means to build a civilization. Stability is no longer a default state granted by nature, but an active achievement maintained through wisdom and unwavering attention. The society that grows under this managed sky would internalize this reality. Education would emphasize interconnectedness and long-term systems thinking. Culture would celebrate not just explorers, but healers and caretakers, those who dedicate their lives to the subtle art of balance. The very concept of progress shifts from conquest to harmony, from dominating an environment to partnering with a creation. In this light, a terraformed Mars becomes more than a second home. It becomes humanity's first great lesson in cosmic responsibility, a test of whether we possess the patience, humility, and wisdom to not just build a world, but to deserve it. The knowledge forged here, the science of planetary stewardship, may ultimately become our most valuable export, the quiet skill that allows us to walk gently among the stars, not as conquerors but as gardeners. Forging a breathable sky is the story of a species learning to think in eons. It is a narrative written not in years, but in the patient rhythm of centuries, a grand tapestry where threads of physics, biology, ethics, and raw human aspiration are woven together across the loom of deep time. Our journey has taken us from the silent, suffocating reality of the present day, through the staggering arithmetic of sourcing an entire sky, past the brilliant and terrifying technologies that could unlock it, and finally into the profound weight of responsibility that such power demands. This endeavor does far more than propose a new world. It fundamentally redefines what we believe is possible, challenging us to measure our ambitions not by national borders or quarterly profits, but by the fate of planets and the turning of geological epochs. The path ahead is strewn with obstacles of unimaginable scale and complexity, from the relentless erosion of solar wind to the ethical quandary of playing creator. Yet, the very act of pursuing this vision expands the horizons of our technology and our spirit. It forces innovations in energy, materials, and artificial intelligence that will ripple back to heal and advance our own world long before the first forest grows on Martian soil. More than that, it offers a rare and powerful gift, a species-wide goal that transcends the conflicts of the moment, uniting generations under a shared story of cosmic stewardship. The red planet becomes a mirror, reflecting not just what we can build, but who we aspire to become, gardeners of a fragile universe rather than mere passengers within it. We would love to hear which part of this monumental challenge captures your imagination or gives you pause. Does the sheer scale of moving planetary atmospheres intrigue you, or does the profound responsibility of designing a biosphere give you the most to consider? Share your thoughts in the comments below, and if you want to join us as we continue to unravel the mysteries of tomorrow's technology, be sure to subscribe.